learning how to. What? All right, lesson 4. Lesson 4. All right. This is going to be so much better for you than this last one anyway. All right, we've so far talked about neutral atoms, of course, and when you're walking down the street and you see sodium, you're like, hey, look, it's sodium atom. That's how it is. It's got 11 protons, 11 electrons. It's fine like that. There's nothing wrong with sodium. Okay, actually, we don't have to talk about that because yesterday we went to the lab and I said, hey, look, it's sodium. Yeah, stick, right? And we put a sodium. Okay, so and that's just sodium by itself, and you could find one atom by itself, and it's probably fine like that. Okay. However, if it can get rid of that extra electron, that valence electron, that one electron, if it can get rid of that one, it will. But it has to go somewhere. It has to be a partnership. So there has to be usually somewhere where that electron goes, and it usually goes to a nonmetal, of course, right? So we're going to talk about ions and ionic compounds today. Atoms are most stable when they have a full valence level. When neutral atoms, which do not have a full valence level, come close enough together, one or more electrons may be transferred from one to another. Right? So, an example would be sodium and chlorine. So, we're going to do electron energy level diagram, a little review from yesterday. So, we're going to put sodium down here. We're going to put 11 protons, 12 neutrons, let's see, 2, 8, and 1. There's my valence electron, yes. Okay. And chlorine, 17 protons. I'll get it right over here. 18 neutrons, 2, 8, 7. That's why I don't want people sitting over here too much, because I'm always late. So, once again, these are neutral atoms. How do you know? Count the positives, count the negatives, right? Look, 11 positives, 11 negatives. 0, right? Neutral. Chlorine, 17 positives, 17 negatives, it's neutral. However, if possible, when they get close enough together, they can help each other out. They become a little bit more stable. To become more stable, there'd be a transfer of electron in this case, or electrons in some cases. So look, if I can get rid of this one electron here, if I can get rid of this one, I'd cut it off here and I'd have a full outside shell. Where's that electron going to go? It's going to go there. And if chlorine gains that electron, it's going to have a full outside shell, and they work together to make, obviously, full outside shell, full valence level shells, and they both become more stable. However, when that electron transfers, okay, it also has something to do with electronegativity, which we'll talk about later on in this unit. So that's a big part of it as well. Chlorine really wants that electron. Sodium really doesn't want that electron. So chlorine's able to pull it away from sodium, basically. But when that happens, right now, you get this. That electron is gone, right? So you get that. And chlorine, of course, what is it? 17 protons, 18 neutrons, 2, 8, and now the outside one also has 8, and they're filled, okay? So, when they come close enough together, this will happen. Okay, chlorine will take that electron, fill its outside energy level, sodium will lose that electron, and now you get this. But the simple math here, folks, says that, look, if I got 11 positives and only 10 negatives, the overall charge on sodium is what? Yes, positive 1, right? So we now need to put a positive sign there to represent the fact that it's no longer neutral. It now has a charge, all right? Here we got 17 positives, 17 protons, 18 electrons. So you do the math, get a calculator if you're not sure. 17 positives, 18 minus 17 minus 18 is somebody else. Huh? -1, yeah. So we're going to say, once again, it's not neutral anymore. A minus sign, okay? And now what's happened is those neutral atoms have changed. These neutral atoms have changed into ions, okay? We can't call them atoms anymore because they're not neutral. They're ions, right? And they hold together very well, actually, as well. Incredibly well, because the opposites attract. You'll find out that positive, negative attraction here So very, very strong. Opposites attract, hold together very well. All right. So that was what makes up an ionic compound, basically. They're both there. They're helping each other out. Okay. So that's an example of sodium and chlorine. Right. I'm going to show you another picture here on the next page. Now you have to keep in mind these are now Lewis diagrams, and we'll do these drawings later. So don't panic if you're not 100% sure what's going on. But these are Lewis diagrams, so only valence electrons. They do the same thing with sodium and chlorine here. See, sodium's got 1 valence electron. Chlorine's missing 1, right? It's 7, just like I showed you on the last one. So there's a transfer that takes place, and you get sodium ions and chlorine, which now has a charge, so therefore it becomes chloride ions. All right. Magnesium has 2 valence electrons. It's in group 2, right? 2 over, 2 valence electrons. If it could get rid of those 2, it would have a full outside shell, right? So those 2 go, in this case, to oxygen. Oxygen is looking to gain 2. It's got 6 valence electrons. If it gains 2, it becomes more stable. It gets 8. So there's those 2 electrons there that have been transferred. Magnesium lost an electron, so therefore it gets 2 plus charge. Right? It was 12 positives, 12 negatives before. Now it's 12 positives, 10 negatives. Do the math. 12 minus 10, 2 plus. Oxygen, okay, was 8 protons, 8 electrons. Now it's gained 2 electrons, so now it has 10 electrons. 2 and then 8 to fill up the outside shell. So now it has a 2 minus charge because electrons are negative. When we write these, this is actually a little bit more for later, but when we write these, the metal, such as sodium and magnesium, lose electrons. They have no valence electrons remaining, therefore we don't write any dots around the symbol, but they are stable, okay, for the metal ion. For the nonmetal, we do. All right, don't worry about that too much right now. We'll come back to that. I think you guys have some definitions to fill in if I'm not mistaken here, so I'll let you do that. All right, so ions are atoms that have an electrical charge because they've either gained or lost electrons. Make sure you know that definition. Ions are atoms that have an electrical charge. Okay, they've either gained or lost electrons. The only reason I put monatomic, I don't want you to know monatomic, but the only reason I put it there is because we're going to talk about polyatomic, so just so you know where that name comes from. Monatomic refers to one atom ions, so things like calcium ion, phosphide ion, things like that, so just one atom. Metal atoms always form positive ions, also known as cations. All right. To name a cation, you're obviously going to just use the name that you normally use. So calcium becomes calcium ion, sodium becomes sodium ion, etc., etc. Nonmetals, you will are also known as, are always going to be negative ions, and they will also be known as anions. And I know what you're thinking. Metal ions or cations, shouldn't nonmetals be dog ions? No. Sorry, dog lovers. Nonmetals form anions by gaining valence electrons to fill their outside shell. The name for the anion has to change a little bit. So this is where, you know, when you look at your periodic tables, which of course you have already, because it's chemistry, but when you look at the nonmetal ions, the name has to change. So things like, for example, fluorine. Well, if I say fluorine, I'm talking about the neutral atom. If I drop the ending and put an "ide" on the end, I'm talking about the ion. Fluoride ion. Okay? So fluorine, fluoride. Chlorine is neutral. Fluoride has a charge. Bromine, bromide. Oxygen, oxide. Okay? Sulfur, sulfide. Those are the differences. Sulfur is neutral. Sulfide has a charge. All right? Make sure you understand that difference, because I often get those interchanged and it's not correct. Okay? Nitrogen is neutral. Nitride has a charge. All right? So make sure you know the difference between those. Most of the "ide" ones, that when we say "ide," I'm telling you right now, if it says "ide," you're looking at the right side, the non-metal part, 99% of the time. Okay, so if I say nitride, go to the right side, that's the nitrogen atom with the charge. Okay. Now, polyatomic, oh, are we done this one? I think so, eh? Oh no. Yeah, we are. Polyatomic ions. You're going to find those in the top left of your periodic table. There's a big list of them there, quite substantial. Probably like about, I don't know, let's guess about 20. How's that? So there's a list of 20 polyatomic ions. Polyatomic ions are atoms that have joined together that can accept, or in some cases, give electrons. Right? That table is arranged alphabetically according to their name. So you might say, well, it doesn't quite make sense that this one's here. If that's the case, you're just going to have to look for it. You know, when we talk about sulfate ion, well, I'd probably start with S. All right. When you talk about nitrate, I'd probably start in the N category, somewhere in the middle there. Borate, I'd start with the B, probably. There's a few goofy ones, like for example, ammonium. It is alphabetically at the beginning, but it's actually NH4+. So there's some that you'll have to adapt to a little bit. All right. Most of them end in ate or ite. Polyatomic ions containing nitrogen. So we'll take a look at this now. That's a good list, but it's not all the ones you need to know. All right. So I'm going to give you a little hint here. You have to write these down. I'll give you a little pattern for the rest of these. Right. So unfortunately, this didn't work out very well. You don't have this, so you're just going to have to write this down somewhere. I'm not sure why you didn't get this, but I'm actually going to just cross these out here because those look a little bit goofy. Okay. So here we have NO4 with a minus charge, superscript. We have NO3 with a minus charge, NO2 with a minus charge, and NO with a minus charge. I'll let you copy those down here real quick. Actually, I'll let you copy those down, and then what I want you to do is look on your periodic table, top left. If you don't have one, grab one over here, of course. Top left, and I want you to find as many of these as you can. So look to see which ones you can find on that polyatomic list, and I want you to write them down beside there somewhere. Okay, so go ahead and find those, write them down. And, no, not you, somebody else. Nitrate, which one's that? Okay, so we'll put a nitrate. I don't care which side you put it on, whatever. Nitrate, I have more room here, so I'll put that there. Is there another one you can find on there? Nitrate? Another one? Ryan? Yes, which one's that? Yeah, NO2 minus, right? So those are the two you can find on the periodic table. And like I said, most of the time that'll be fine. But you have to understand how to adapt the rest of these to fit into here. Because obviously NO4 minus is not on there, I'll tell you right now. And neither is NO minus. So there is other ones. You'll notice that these are all nitrogen. They all have oxygen. Just a different number of oxygens. They all have the same charge. They're all a -1 charge. That never changes. The only thing that's changing here is the number of oxygens. So when that happens, you need to be able to adapt it according to this little thing here. Well, I can tell you, if this is nitrate, and one extra oxygen, therefore, would be per nitrate. Okay? Anybody do this last year or no? No? Okay, that's good. See, you're learning something new. Woohoo, eh? Yippity-doo. So that would always be per nitrate. So one extra oxygen is going to be, if nitrate's NO3, if it's NO4, that's per nitrate. Okay? Got to put a per in front of it. If this is nitrite right here, and that's NO2, one less oxygen is hypo nitrite. Okay? Not hippo, that's different. Hypo. Okay? Hyponitrite. That's the pattern they always follow. Right? So we're going to do another one now. And I'll show you a little bit of difference here. Okay? Good? Alright. Let's do this one. PO4 3 minus, PO5 3 minus, PO3 3 minus, and PO2 3 minus. Notice these all have P's. They'll have a different number of oxygens, but the charge is the same, of course. All right. So go ahead and try and find any ones that you can find here on your periodic table. I'll give you a hint. Start looking in the P section. You find on this one. Phosphate. Which one's that? Yeah. So this is phosphate. Can you find any other ones on here? Is there any other ones? Is there PO5 or PO2 or PO3? Yes? No. So that's okay, because that's all you need. All right. After that, after you know one of them, the rest have to kind of fall in that same order. So I know that if this is phosphate, one more oxygen is per phosphate. Right? There's phosphate. One less oxygen is phosphite. One less oxygen than that is hypophosphite. So they always follow that pattern. You might say, well, what about PO3 minus? And the answer is that's as far as we go. Okay. So based on that, you can adapt it to what you need to have. Okay. So don't forget that when we get to the naming compounds thing. Unfortunately, last class I got. Can I do one more and then I can tell you my joke? Oh, yeah. So this one's, load this one up, it's sulfate. They didn't laugh at this one. Maybe it's because we're just really nice, I don't know. But that's okay. That's sulfate. What's the next one? What's that one? Sulfite. Sulfite by the micrograph after school. Don't do that. Sulfite. And then, of course, hyposulfite would be underneath that, and persulfate would be above that, right? So it still follows the same pattern. You'll notice they're all S's, they're all O's, they all have the same charge, just different numbers. The important thing that you have to understand here, though, and the reason I gave you the other one is because it only had one. It doesn't matter. You can find one, and from that you can adapt it. But listen, nitrate here doesn't mean that you have 3 oxygens. So look, nitrate is 3 oxygens here, yes? But phosphate is 4 oxygens here. So the same ending has a different number of oxygens for this one. So what I'm saying is, just because it ends in 8 doesn't mean it's 3. It could be 4, all right? Usually it's not any other number than those 2, but you have to look it up on the periodic table and use that to adjust accordingly, okay? So just don't assume that all 8s are 3 oxygens, because actually quite often they're 4, right? All right, let's go here. We missed this one. Ionic compounds we'll talk about. Ionic compounds are made from simultaneous attraction between cations and anions, so positive ions and negative ions, of course. Cations and anions combine together in the lowest whole number ratio, and their sum has to be 0. You've heard the term swap and drop probably, yes? Swap, drop. I like to add on to that. Swap, drop, and roll. No. Swap, drop, and reduce. Okay? Lowest whole number ratios. I'll show you a case where that happens later on. Swap, drop, and reduce if you can. Okay? That's what we're really talking about when the sum has to be 0. Alright? When writing the formula, obviously the metal always comes first. Look at the periodic table. All the metals are on the left side. You know, English, when we read books, we read left to right. So metals, non-metals. Alright? So, so we're going to name some of these, and then I'm going to give you a little sheet here to do some work and give you a little practice here just for a little review. Some of this you'll be like, this is too easy. That's fine. Tomorrow, double-sided sheet. See how fine it is. All right. So when you're, we're going to write out the formula for this, swap and drop, and we're going to write out the name for these as well. I might as well get practice with that. Swap and drop says you basically take the charges and you swap them and you drop them, right? So the 1 plus comes over and down, the 1 minus comes over and down. So when we write out sodium chloride, 1 comes over down, 1 comes over down. We don't write 1s because you're chemists and you're lazy, and that's okay. 1s take too long to write, all right? We don't have time for that. Chemist. All right. This, of course, is made up of sodium ions. We call sodium ions, or we call the sodium ion sodium, of course. And it's made up of chlorine atoms with a charge, so therefore we have to drop the ending. Chlorine becomes chloride. All right. Sodium chloride. All right, swap and drop. This one here. Okay, aluminum 3 plus, chloride 1 minus, swap and drop. That's going to come over and down. That comes over and down. So okay, now 3 comes over and down. 3's here, over and down. 1 comes over and down. We don't write the 1. Okay, it takes too long. So in this case here, we have the aluminum 3 plus ion, but we use aluminum. And of course, chlorine has a charge, so chloride. Chloride. Okay. Remember, lowest whole number ratios, swap and drop really comes from this, right? If you have an aluminum 3 plus, how many Cl minuses do you need to make it back to 0? Because ionic compounds, when they're combined, they have an overall charge of 0, right? So 3 chlorides, right? 3 plus, 3 minus, yes? 0. They should equal 0. Aluminum 3 plus, oxide 2 minus, swap and drop. Okay, now O, 2 comes over to here, down, swap one over, 3 comes over there. That's made up of aluminum ions and oxygen with a charge, so oxide. Aluminum, oxide. Okay, good. Now we're going to do some more naming stuff tomorrow, or maybe later today, we'll see. But aluminum oxide, good? Yes? Okay. Once again, I'm sure most of this stuff's review. We'll really get a good sense tomorrow after tomorrow's homework sheet. You'll get a good sense of if you know how to name these properly or not. Trust me. Polyatomic ions. So more than one atom combined together with a charge. You may have to use brackets. When do you use brackets? When it's 2 or more. Okay? So if you need to put a 2 or more around a polyatomic ion, you need to have brackets. Right? That's going to come with a little bit of practice and maybe just a little bit of understanding too, but nonetheless. Lithium, and we got carbonate here. So lithium carbonate. Lithium's a 1 plus, that's going to come over and down. It's a 1 that's coming around this thing here, so I don't need brackets. The 2 minus is coming over and down, and this is just one atom by itself, so I don't need brackets, I just need to put the 2 there. Okay? Once again, 2 lithiums, right? And one of these go together, yes? Overall charge is 0. Swap and drop, that's where it comes from. Ammonium is this one here, NH4+. If you're not sure, look, a bunch of atoms with a charge. Where should I find that? Top left, right? Periodic table. When I say top left, I mean top left of your periodic table. NH4 and S, right? So 1 plus, over and down. 2 minus, over and down. So 1 comes over, I don't have to write that. 2 comes over though, look, bunch of atoms here, polyatomic, I need 2, so I need to do that, right? Brackets and a 2. Once again, NH4 all combined together is looking to get rid of an electron. I'm going to show you that diagram later this year. You're going to draw it for me, okay? I need 2 of all that, right, to go with 1 of those, yes? Okay. Once again, the charges have to be 0. If they're not, then it's not right, I can guarantee you. The last one here, once again, oh, I should name that one, eh? Sorry, just getting excited. Ionic compounds will excite me a little, I'm not going to lie to you. They're pretty exciting. I like them. Opposites attract, strong, positive, negative. Anyway, 1 over 2, okay, like so. I'll go back up and name those ones. Okay? These are probably even maybe, I don't know, maybe even easier to name because basically the names are right beside them on the polyatomic section there. So this is lithium. And that, of course, is the carbonate ion, so we call it lithium carbonate. This is ammonium. And that S2 minus was sulfur, so now it is sulfide. Okay? This is ammonium. And of course, CO3, that charge of carbonate. You'll get good at all these polyatomic ions if you really know them, or if you kind of forgot them over summer. You'll get pretty good by the end of tomorrow, I'm sure. Okay. Good. Any questions? Just a few more real quick here, and then you guys get some work time here. We're going to talk about transition metals, okay, multivalent metals and ionic compounds. So when you're in that group 3 to 12 section, right, 3 to 12, you really got to pay attention because quite often most of those, like copper, has more than one charge. Copper, 1 plus and a 2 plus. Right? So you have to tell me which one you're using. Nickel has more than one charge. Iron has more than one charge. So you have to represent that accurately. Okay? You can't just say it's iron oxide because I don't know which one you're talking about. So iron, 2 plus, oxide, 2 minus. We're going to write out the formula for that. 2 plus, 2 minus. Right? Iron loses 2 electrons, oxygen gains 2 electrons. This is what I'm talking about, swap, drop, and reduce, okay? 2 plus, 2 minus, I can swap them, 2, 2, those reduce both down to 1, 1, yes? So, how many, you know, once again, how many of these do I need to go with those? Well, that's a 2 plus, that's a 2 minus, I need 1 of each, right? All right, this iron's gonna lose 2 electrons, that one's gonna gain 2 electrons, 1 of each, that's it. So, this one here, I'll just leave it like that. Swap, drop, and reduce, right? So swap and drop, 2, 2, reduces down to 1, 1. This one here, obviously different. 3 comes over and down, 2 comes over and down, yes? Different formulas. They have different properties. They have different types of, they probably have different melting, I know they have different melting and boiling points, different solubilities perhaps. They're very, very different, okay? So, please, please, please make sure you include Roman numerals when you have to name these, obviously, to tell me the difference. This is iron 2 oxide. Use Roman numeral 2 because, of course, you're using the 2 plus charge. The other one is iron 3 oxide because you're using the 3 plus charge of iron for this one. Okay? So make sure you use the appropriate Roman numeral. If you don't know the Roman numerals, there's a thing called Google, and it probably will tell you. Okay, yeah. So make sure you learn them if you don't know them. Obviously, 1 looks like an I, and 2 and 3, 4 and 5 and 6 maybe is all you got to go to. So I'll leave that to your kind of own stuff there. All right. So there's that. All right. You're gonna get a worksheet that looks like this pretty soon. You don't have it yet, so just relax. It's pretty straightforward. You're going to fill it in. So here, for example, zinc ion, you're going to look up the zinc charge here. Chloride, you'll look up the symbol and the charge for that. You'll write the formula, swap and drop. This one here, do not forget, for example, this is iron 2 plus. So when I write iron, iron comes in more than one charge, so you should call this the iron 2 ion. Okay? Make sure. So if there's more than one charge, you make sure you put that in the name. All right? Now you might say, what does that go with? Not everything transferred over onto mine, so don't worry. When you get your sheet, all the stuff will be there for you. Subscripts didn't happen here and stuff like that, so when you look at these, it's going to be a little goofy. When you look at your worksheet, it'll make sense. Okay? They're there for you. Look, this one looks dihydrogen phosphate, dihydrogen, di. It sounds complicated because it probably is complicated. So look in the top left, polyatomic ions, and you'll see somewhere dihydrogen phosphate. Is it under the D's? I'm going to tell you right now, probably not. You're going to have to look for it. Okay? So some of that will take a little bit of time for you. One more thing. Okay? Okay. So you got your periodic tables there. You know, over on this side here, you'll notice all the charges are there for you, right? So we know that calcium, for example, has 2 valence electrons. Oh boy, wouldn't it be nice if I get rid of those 2 so it forms a 2+ charge, yes? Because 2 electrons go away, you have 20 positives, you have only 18 negatives, and you do the math and it's a 2+, right? And we know that potassium will form a 1+1 because it has 1 valence electron. It's looking to get rid of that. And then you go to, like, for example, iron, and you say, oh geez, it could be 2+ or 3+ depending on stuff, okay? And you use those 2 and you don't have to worry about why or anything like that. However, look over on this side, the nonmetals, look on yours, you see a bunch of dashes, yes? They used to, but they do no longer put these charges in there for those, okay? Because they expect you to know these, and we're big boys and girls now, so we can know these. Look, everything's trying to become like the noble gases, right? To become more stable. So when you think about fluorine, how many valence electrons does fluorine have? Fluorine. Page. 7. It needs to get how many more? 1, right? So what charge is fluorine going to form? It's going to form a -1. It wants to gain 1, yes? So guess what? Chlorine has 7 valence electrons. It wants to gain 1. Bromine has, well, it gets a little tricky in here, but basically 7 valence electrons. Or 17, but 7. It's looking to gain 1. Bromine wants to gain 1. Iodine wants to gain 1. Astatine wants to gain 1. So those all form -1 charges. You can in fact put that at the top if you wish on your periodic table. Just remember, you don't get that one for your quizzes and tests. You need to know that, okay? These all form -1. Think about oxygen. How many electrons is it short? Oxygen is short how many? 2. So it wants to form a 2- charge. It wants to gain 2 electrons. So oxygen and sulfur and selenium and tellurium all usually form 2- charges. Okay? They always want to gain them. Nitrogen, how many does it have to gain? It's not a trick question. 1, 2, 3. Okay, so it wants to gain 3. So it forms a 3- charge. So nitrogen, phosphorus, arsenic usually form 3- charges. Carbon, ooh, wants to form what? Carbon and silicone usually do not form ions. Because when you think about carbon, how many valence electrons does carbon have? So does it gain 4 or lose 4 is the question. Well, we'd probably say it would lose 4 or gain 4, I guess, because it's on the non-metal side. But they usually don't form ions. Carbon and silicone are very good for molecular compounds, sharing electrons. Okay? So most of the time the carbon doesn't have the electronegativity, if you want to say, which you'll learn about later, doesn't have that ability to pull in all those electrons close enough to it to steal them. They want to share them. Okay? So probably 2 more, we're going to look at molecular compounds as well. And a lot of them have carbon type of based things. Okay? Carbon is very good at molecular compounds. So we usually don't do that one, okay? Having said that, there is a carbon one. It's a polyatomic ion in the top left. It's actually called carbide, but it comes in 2s and it has a 2- charge, and we usually don't do that one, okay? But that's carbon silicon. But you have to know those other charges, okay? So obviously no charge, right? Because these don't want to gain or lose. This is -1 row or column or whatever, -2, -3, okay? And you just have to remember that. The confusing thing is when you look at your periodic table, I wish they wouldn't have done this. They put dashes in there. So everybody thinks they're all -1s, but they're not, okay? So they just put, like if you look at oxygen, there's a dash there. I wish they would have just left it blank, but they didn't, okay? So it is what it is, all right? So go ahead and start working on those. And if you got any questions,